well, not only with technology, but we will talk about these things. So I am going to be using Desmos to show you some of these graphs. So for example, f of x is equal to 2 to the power of x. So the exponential functions, you'll notice, are b to the power of x. So a base to the power of x. So normally we had x within our variable, where it was like, oh, quadratics were x squared, or linear was y equals mx plus b, right? But the thing that makes exponentials different is that the x is no longer part of the base, but it's actually the exponent of our thing here. So it's 2 to the power of x, which changes our graph a lot, right? So that's going to be a little bit different with about how it looks like on a graph. I like lost words for a second there. So let's try to graph this on Desmos, and then we're going to copy it down on our graph here. So I'm going to do it half and half here. Okay. So on Desmos here, if I graph f of x is equal to 2 to the power of x, we get a graph that looks like this. Okay. And there is one key point that you have to understand is 0, 1. Why is this point important? Anyone have an idea why that might be important? Y-intercept, absolutely. And what makes this so important with this y-intercept, 0, 1? It is most definitely the y-intercept. So if this is 0, 1, that means x is 0 and y is 1. What happens when x is 0 for our case here? What do we get when x is 0? At f of 0, what happens? 2 to the power of 0, which means anything to the power of 0 is 1. That's one of the exponent laws that we talked about, right? And the reason why that's important is because when I give you, let's say, another function like y equals 4 to the x, you'll notice that in this case, the y-intercept would be exactly the same. When x is 0, y is going to be 1, because everything to the power of 0 is 1. So the reason why this y-intercept is important is because it's consistent. That point doesn't change for a base exponential function. So that y-intercept is consistent. Next, you can do a table of values here if you wanted to graph out using a table of values. So for example, on the left, if I were to draw a short table of values here, like x and y, and I did -2, -1, 0, 1, 2, I would get 2, 4, 1/2, and 1/4. And that can be shown on our graphs here. I'll draw those points so that you can see it. And I'm going to label it. So 1, 2, 2, 4, -1, 0.5, and -2, 0.25. So as you can see, these 4 points are on our graph, and we can graph that as well on here. So 1, 2, 2, 4, 1, 0.5, -2, 0.25, 3, 8, and then we would draw our graph like so. And this is really hard to graph. Or at least I'm having a very hard time graphing this. I hate tablets when I draw graphs. Okay, that's the first part. And it goes infinitely towards the left. It doesn't actually cross the x-axis here. Anyone have an idea why it might not cross the x-axis? Why would it not cross the x-axis?
Mr. Choi, I don't really understand like how did you get these points? Like I don't understand how you got this.
When you plug it into x here, right, into 2 to the power of x, 2 to the power of 2 is 4, 2 to the power of 1 is 2, 2 to the power of 0 is 1, 2 to the power of negative 1 is 0.5, so on and so forth. So plugging in the points, you should be able to get your values here
Whenever
using
we're
this one.
graphing, we should put in those points on the x value.
Yeah, that's essentially your goal here. When you're graphing it using a table of values, usually -2 to +2 is a good measure of what you want to do. What makes this hard to graph though is that when you go into the negatives for positive bases, we get decimal values, and that's not exactly something that's nice to graph at times. And I'm sure we'll see examples of that in the future. Okay. But for now, we want to see what does this exponential graph look like? And it makes sense, right? It's exponential graphs, they get significantly bigger over time. Like I'm sure you've seen those situations like is it better to get $10,000 straight up or is it better to get $2 on the first day and double that the next and so on and so forth for the whole month? And the whole thing of that was, yeah, it's better to get double every single day because you'll get way more than 1,000 by the end of the month, and that's because it increases exponentially. We see an increase, and that curve sharply spikes up because we're multiplying by 2. We're doubling every single time. So the next one would be doubling, that would be 8. Doubling that would be 16. Doubling that would be 32, 64, 128, and it starts to climb really quickly in comparison to something we've done already, like for example, a quadratic, which didn't really, it did increase faster than a linear, of course, but it didn't increase as fast as something compared to an exponential that's actually doubling or tripling or things like that. So the first one here, 2 to the power of x, we see this kind of graph here. The opposite, so is this a increasing or decreasing function? Looking at it from left to right. Sorry, say that again, Sydney.
Increasing?
Increasing, absolutely. Yes, this is an increasing function. Increasing function goes up from left to right, right? So as you're reading graphs, as we do in Canada, in the Western world here, we do read things from left to right. So understanding from left to right, it is increasing. It's going up towards the right. So that's going to be an increasing function. And so for example, if we fill out these tables, like we said, we plug it in. So if I zoom in all the way in here, like 2 to the power of 0 is just 1. 2 to the power of 1 is 2. 2 to the power of 5 is 32. 2 to the power of 10, then we start needing a calculator. 1024. And then 2 to the power of 20 would be 1 million. I think it's 1 million. Yeah, there it is. So 2 to the power of 20 is 1,048,576. So as you can see, by just even hitting x equals 20, we get a significantly bigger values than if we were to do like x squared, like 20 to the power of 2. Completely different. Right? So that's what happens as it goes to the right. We see the numbers spike up very quickly, right? We see 1, 2, 32, 1,024, and then 1 million hits you right in the face really quickly. On the other side, though, if we were to go to negative values, 2 to the power of -1 is 0.5. 2 to the power of -2 is 0.25. 2 to the power of -5 is going to give us 0.03125. 2 to the power of -10, if we were to do that here, would give me 0.0009765625. And I think you can only imagine what 2 to the negative 20 would give us. 2 to the negative 20. If you do that on a scientific calculator, you should get scientific notation. But if you do this with just decimals, I'm going to show you how small it gets. 0.000000953674,316. As you can see, very, very small number, right? Using your knowledge of, right? Using your knowledge of the negative exponents, let's understand why this happens. When we have 2 to the power of negative 1 and we use the negative, we flip the base and leave the fraction. Does that make sense? Right? We use the negative, flips the base, and then we leave the exponent. So that's why it gives us 0.5, because 1/2 to the power of 1 is 0.5. If we do 2 to the negative 5, we're essentially saying it's 1/2 to the power of 5, which is just 1 over power of 2 to the 5, which is 1 over 32, which gives us 0.03125. So this is what happens. That negative is causing us to multiply halves together, which makes it very, very small, right? What's half of that? And then half of that, and then half of that, and then half of that. And we repeat that over and over and over again. So if we do 20 halves of a half, we get an extremely small number, right? But the important thing that you have to realize is you will never hit 0. It is impossible to hit 0 using an exponent. You can make the number extremely small. But my question to you as a class, I want you to think about this. What part of a fraction makes the fraction 0? The numerator or the denominator? Which one makes it 0? The numerator or the denominator? What makes a fraction turn into 0? We got people guessing denominator. The answer is numerator. When I ask you on a test, like, oh, what did you get on the test? And you say 0 out of 25, that fraction is 0 over 25. That's a 0%, right? It's the numerator that tells you that a fraction is equal to 0. The denominator just tells you how small we can go. So the bigger the denominator gets, the smaller the fraction gets, right? 1 over 25 is a significantly smaller size than 1 over 5, for example, but it's not 0. I can do 1 over 1 billion. It's technically not 0. It's an extremely small number, right? If I said I have a large pizza and I sliced it up into 1 billion slices, and I say, here's one slice, how small is that slice? It's a tiny slice. I don't know how I'm going to cut a pizza into a billion slices, but it's not 0. If I give you one slice, it's still one slice out of a billion slices. However, the only way to make a fraction 0 would be to say, I'm giving you nothing. 0 out of a billion would be 0. So as a result, it's important to understand that exponential functions, it is literally impossible for them to cross 0 or hit 0 without transformations. Because the exponent does not change the numerator. What the exponent does is it only changes the denominator, as you can see. It only affects the denominator, so it never hits 0. That's a very important quality here that we want to understand. Okay. So to answer this next question here, which is what happens to the value of 2 to the x, we went over these questions, so we're going to go over it now. What happens to the value of 2 to the x as the value of x gets very small? It becomes, okay, hello? It becomes, okay. It becomes smaller and closer to 0, but not actually 0. Okay. So as we go into the negative x's, we notice that it becomes smaller and smaller and closer to 0, but it never hits 0. Will the value of 2 to the power of x ever equal 0? Never. Never. The x variable would make, actually, let me type this out. I don't know why I'm writing it out like this. Let me type this out. Might be faster. So the reasoning, just to re-explain, the x variable would only affect the denominator of the fraction. To make a fraction equal to 0, we need the numerator to be 0. Okay? Any questions about this? We're going to go over more examples within the lesson, but any questions so far about these interesting maybe to some of you, hopefully, fingers crossed, but the important properties of this exponential function here, right? 0, 1 is a common y-intercept. The function never hits 0. It can get really small, but it'll never hit 0. Okay? And of course, it increases exponentially so far, as we know it. So then let's move on into another type of exponential function. Oh, wait, we still have a couple more questions. Whoopsies. Are there any values of x that would make f of x equal 2 to the power of x undefined? Is there a number that would make this impossible? No. All values of x would exist. No, it doesn't matter what you plug in. All values of x would exist. So in other words, domain, what's the domain? It's XER. There's no limit to what x can be. What is the value of the y-intercept? It's 0, 1, as we saw. So someone want to give the domain and range for this? Anyone want to give it a shot? I'll bring up the graph here. It goes infinitely both ways. Anyone want to try domain and range for this?
XER, YER?
So XER here, and the second one you said YER?
Yeah.
There is a restriction here. There is a restriction. Anyone else want to try?
But you said it goes infinite both ways.
Right. For the x, it goes infinite both ways.
Oh. Would it be such that y is always going to be greater than 0?
Greater than 0. Sorry, not equal to. Greater than 0. Yes, that is correct. It cannot cross 0. We said it never hits 0, so it's above the x-axis at all times. Right? So just to show you that example, if I go all the way down to like negative 100, it says 0 here because Desmos has to round it down to 0, but it's actually an extremely small decimal value. So as a result, y is greater than 0 is actually what you're going to write here. Do not write equal to. It does not equal 0. It's greater than 0. That's it. So that is your restriction for your exponential function. Any questions? Going once. Going twice. Okay. So now let's use decimals to graph our second one, which is we're going to graph both 2 to the power of x as well as 0.5 to the power of x. So first, 2 to the x, we know how to draw it. So we saw before it was here, 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 and we saw it increase exponentially like this. And in purple, I'll draw 0.5 to the power of x. So 2 to the power of x versus 0.5 to the power of x. So the blue line on the right is 0.5 to the power of x. Notice how it has the exact same y-intercept as we stated before. It has to be, right? Anything to the power of 0 is 1. So they are going to share that y-intercept. The difference, though, are the points on this graph. Anyone have or notice anything special in particular on this graph between these two?
It's just
There's a special one.
Isn't it reflected like just negative?
Yeah, it is reflected over, right? If the y-axis was our axis of symmetry, it's symmetrical. It looks symmetrical, doesn't it? Which means our graphs would be the opposite of what we expect. Like so. So the purple would be our 0.5 to the power of x. And in red, it would be 2 to the power of x. Now, why would that be the case? Anyone have any suspicion as to why that might be the case? Why is it the complete opposite of this? Well, what is 0.5 as a fraction? 1/2, exactly. So if we say 0.5x, or to the power of x, is equal to 1/2 to the power of x, what happens if we had 1/2 to the power of -2, for example? Well, what does the negative do? It flips the fraction. So 1/2 becomes 2 to the power of 2. 2 over 1. That equals 4. So notice how that works. So because the fraction itself, 1/2, gets flipped with the negative x value, we get a positive number, right? And that's going to be the case if we start going into the positives and so on and so forth. So it's going to be that flip because we have the reciprocal of the base 2. Which means if we were to kind of expand this idea, then if we call this quote unquote opposites or reflections of each other, then we could say 3 to the power of x would be the reflection of 1 over 3 to the power of x. 4 to the power of x would be the reflection of 1 over 4 to the power of x. And so on and so forth, right? So that's the connection they want you to make here because of how negative exponents work. The reason why we went over those exponent laws was to show you that, wait, if you do negative numbers, it flips that base. So they're going to be opposites of each other, right? If you have a positive base with a negative value, it's going to be the fraction. If you have the fraction with the negative exponent, it's going to be the positive. It's going to be a non-fraction, the base itself, so on and so forth, right? So that's the connection we want you to make here, or that I want you to make here, with understanding how do these even connect. It's still an exponential function. It's just that we have that kind of shape in the opposite direction like this, right? And of course, same idea, it never hits 0. So, next question. Is 0.5 to the power of x increasing or decreasing? Looking at the purple dots. Going from left to right, is it increasing or decreasing? I have one person saying increasing, one person saying decreasing. Does anyone want to break the tiebreaker?
Increasing.
We got 2 for increasing, 2 for decreasing. That's funny. This would be, and we have a third person saying decreasing. Yes, this is a decreasing function. It goes down from left to right. So this would be a decreasing function because we start high and then we go low as we go to more towards the right. So we're going down. It's like a roller coaster. If you were to go down on a roller coaster on this from left to right, it would go down.
But
Right?
Mr.
The
Choi,
red would be going up.
it's a negative, right? So wouldn't it just be increasing because it's going to like 2 to the other, like to the positive? So wouldn't that be increasing?
So when we're talking about increasing, decreasing, we're looking at the shape. And if we do positives here, if you're thinking of values, if you do 1/2 to the power of 2, that's 0.25. It gets smaller.
No, but
Because
I was
once you go
how
into
it's like a
positive
negative. When you like when it goes, it's gonna go to positive on the other side of the values.
right. But remember, we're always going from left to right when we read a graph. We don't go from right to left. Always from left to right. Just like you would like read a book. So always from left to right. So this would be decreasing. So if we fill in the values here, you'll notice it's literally the exact same things that we did before. So 0 and 1, this would be 0.5, this would be 0.0325, and I think the previous one before that was, let's see up here, 0.0097652625. Like, we're essentially copying those tables down, except you'll notice that when it was negative for 2 to the power of x, we're writing it for the positives because our base is a fraction this time. And for the other ones, right, it would be 2, 4, 32, and then 2 to the power of 10, 1024, and then 1,048,500, I forget, 576. Okay. So what happens to the value of x as the value of x gets very large? What happens to the value of 0.5 to the power of x? It gets smaller and smaller, closer to 0. And as the value of x gets very small in the negatives, what happens? It gets bigger and bigger, doubling every time. Doubling, right? So it does the opposite of exactly what it did when it was 2 to the power of x, as we've been explaining and sharing so far. Any other questions? I hope I clarified the increasing, decreasing, because that was a good question to clarify. Any other questions about this? Okay. So will this value ever equal 0? Anyone want to give this a shot? Yes or no? No is correct. Rena and Sydney, thank you. No is correct because same thing as before. The x variable would only affect the denominator of a fraction. Right? And are there any values of x that would make 0.5 to the power of x undefined? No, all values of x exist. There's no restriction on that. And then what's the value of the y-intercept? 0, 1. We know that. Okay, so notice how these answers are consistent, right? It can never hit 0, all values of x exist, and the y-intercept is 0, 1. So those are consistent properties between exponential functions, right? So regardless of all the exponentials that we're going to look at, these facts don't change, okay? So then we continue onwards here. Domain and range. Anyone else want to give this a try?
Mister, can you bring it up?
Yeah.
Okay.
Anyone else want to give domain and range a try? Anybody? Domain and range? Perfect. Thank you.
Thank you.
All right. Domain XER is correct. And then we have YER such that y is greater than 0. It's the exact same thing. Nothing has changed from the previous one for the domain and range, right? Okay. So in number 7, how does it compare? We said they look like reflections of each other, right? As one goes up, the other goes down, so on and so forth. And we're going to skip number 8 because we're just going to summarize that in our table in below here. We're going to summarize this in our table. Okay. So number 8 here is explain the similarities, differences between the exponential functions. Let's just summarize it. So was 2 to the power of x was increasing, while 0.5 to the power of x was decreasing. The y-intercept was exactly the same. The domains were exactly the same. X is any real number. And the range was exactly the same, where y is any real number such that y is greater than 0. So that hasn't changed here. Okay? I'm going to write that R a little bit neater. Okay? So I wrote less than. What is wrong with me? Greater than, please. Brain work. All right. So in summary, some of you might be like, can you summarize it? And here we go. This is the summary. That's why we're summarizing it at the end here. So in summary, for 2 to the power of x, it's increasing. 0.5 to the power of x, it's decreasing. 0, 1 is always the y-intercept. XER, range is this. So now, let's try to expand and hypothesize and try to guess what would be true for any value of b. So if b is greater than 1, so anything greater than 1, would this be increasing or decreasing? Increasing is correct. Increasing function. And if b was a fraction less than 1 but greater than 0, we would expect it to be decreasing. And I think you guys can see where this is going. The y-intercept is always 0, 1. The domain, XER, and the range, YER, such that y is greater than 0. And there we have it. So there's our summary. So regardless of whether or not it's a 2 or a 0.5. If I graph multiples of this, we should be able to see and understand that it's going to be consistently the same. So I'm just going to zoom that out here on the left side. So for example, if I graph 3 to the power of x, or 10 to the power of x, or 5 to the power of x, look, all of the graphs do the exact same thing. They increase going to the right, they have a y-intercept of 0, 1, and they're always greater than 0. Y is always greater than 0. If I were to graph the fractions less than 1, so 1/2 to the power of x, 1 over 10 to the power of x. We can even do fractions in between. 2 over 3 to the power of x. Look, their graph, y-intercept is always 0, 1. They are decreasing going to the right, and it's always y is always greater than 0. Right? So these are the important properties of an exponential function. Once again, assuming no transformations are being done. Okay. So then we have some homework and classwork questions. So we'll do some of these together before I send you off to do the rest of the work on your own here. So we have functions here, right? We have figures and graphs on a graphing calculator here. And it's asking us once again, can you fill in the table of values using the function itself, right? You'll notice that it tells you the value of the function when x equals 4. So this is essentially saying that a point on this graph is 4, 256. And then same thing here, this is like 4, 1296. So if we look at, for example, figure 1 here, what's the value of y at f of 0? Good, we have 1. So that's going to be 0, 1, so that's going to be 1 here, right? And I think everyone knows that that's going to be true for all of them, right? Right? We learned our lesson today that everything should be 1 here, 0, 1 for every single one of these graphs if it's an exponential function. Yes? Okay, I'm assuming everyone is nodding and saying yes. And then we look at, okay, what's the value of f of 4? So for us looking at figure 1, the value at x equals 4 is 256. Okay? So now the question is, what's the base? How do we figure that out? Yes, we have the instructions here on the hint, right? So essentially what we have here is I pretty much told you for the first one, for question 1, I've said, oh, f of 4 is b to the power of 4, which is equal to 256. Can you solve for b, is what I'm asking you here. Yes, you can do that. Yes, there's an easy way to do it, which allows you to use your calculator. If you can use your calculator to do the fourth root, you will be able to find b. If you don't have a calculator that can do the fourth root very easily, if you don't have that button, then you have to guess and check. Essentially, you have to say, oh, b times b times b times b is equal to 256. So I need to multiply a number by itself 4 times to get 256. So if I was to do it on my screen here, oh, I did 5. 5 times 5 times 5 times 5 is 625. That's a little too high, so I'm going to drop it down. 4 times 4 times 4 times 4. Oh, that worked out, so it must be a base of 4. So what's my equation? F of x is equal to 4 to the power of x. Okay? If you don't have a calculator that can do fourth roots, not much you can do other than to guess and check. Right? You have to work with guess and checking. Okay? Question 2. I want everyone to type the answer in chat. Every single person. On the count of 3, I want you to type it in the chat. No matter how small or how big we make the value of x, the y value of an exponential function will never equal blank. In 3, 2, 1, go. Type your answer and send it. Come on, people. The y value will never equal. Man, you guys are sad. Come on, let's get the answers coming. Come on. That's it. Let's see those answers. Yes. 0. It will never equal 0. That was the main rule that we said, right? Very good. They will never equal 0. Exponential functions never equal 0 as long as there's no transformations, right? Okay. And the rest of these I would like you to fill out and solve. And this will be your homework check for tomorrow. Okay. We do have a question from the textbook that I would like you to do as well. Page 423, numbers 2A and E. But I would like to at least see everyone fill in the table and answer question 3 to make sure I know that you have understood the concept of exponential functions. So I'm going to put that up as an assignment on Google Classroom now. I'll take like a picture of this section here or of this page for you to see. Okay.
Do we have to submit it by tonight?
Please submit it by tomorrow morning before class. Okay? So tomorrow morning before class. It's short. This should take you like less than 10 minutes, to be honest with you. 7.5A homework check.